Welcome everybody to a journey through advanced manufacturing in 2021. My name is Karim Gench. I am the business development manager for the Simpleware group at Synopsys. This is the fifth webinar in our series out of five, and the title will be FE meshing of the part, FE simulation and validation testing. The speakers today will be Thomas Spricka, who is a senior application engineer at Synopsys, Sunil Acharya, who is a lead application engineer at ANSYS, and Matt Sanders, who is a principal at Stress Engineering Services. So this is a recorded presentation with a live Q&A. Attendees will be muted throughout, and you could submit your questions on the right here in this box, the GoToWebinar question box. So we'll try to get through as many questions as possible. So if we can't get to your question, we'll follow up with an email afterwards. And this webinar is being recorded and will be made available to all attendees and people who registered for this webinar series. So if you have any problems, please report these in the Q&A toolbox. So on the left, you'll see the overall workflow, which I hope you're pretty familiar with all of the different partners and the different parts of the workflow that we've been working on and working through in this webinar series to educate the community on this, what we feel is an optimized workflow for additive manufacturing research and development. So on the right is the webinar schedule, and today is June 10th, and next week, in 2 weeks, we'll be having our panel discussion to bring everybody back together to discuss this overall workflow. So I'm pretty excited today to have kind of the culmination of a lot of the work that we've been doing with the image-based simulation to compare to the design-based simulation, as well as the testing of the real-world performance of this part. So to give you an overview of the webinar, 6 industry leaders took on the challenge to develop a clean slate rapid design of an advanced heat exchanger, leveraging each of the advanced capabilities that their companies offer. So this is Topology, ANSYS, EOS, North Star Imaging, Synopsys, and Stress Engineering Services. And this was all inspired by this heat exchanger on the right in gray. So this is the original heat exchanger design, and we thought we could make an improvement on this. And we could leverage each other's technologies to demonstrate an ideal workflow to do this optimally. And you can see in the blue is the design of the final heat exchanger. So just to give you some results right off the bat, we're able to reduce 40 parts to a single part. We doubled the heat transfer in 20% of the volume. We did a 9 times reduction in pressure drop. We did a successful print on the first attempt, a full NDE inspection with 0 defects, and a full heat transfer simulation of the as-built part. So we're really excited with these results, and we're excited to show you these throughout this webinar series. So just to give you an idea of the description of these legacy heat exchanger designs, today's most advanced applications, they are pretty space constrained, and rising thermal requirements are driving the need for smaller and more efficient designs. And there hasn't really been too much innovation in the geometries of most of these common heat exchangers. Most liquid-liquid heat exchangers are dominated by pretty inefficient tube and shell geometry designs like what you see on the right. So this is a cut halfway through one of the heat exchangers. So with advanced manufacturing, a designer can make a heat exchanger with higher energy efficiency and system performance, and is fundamentally able to move larger amounts of heat around using less material in less space. So well-known techniques for convective heat transfer enhancements include the use of structures that induce mixing and swirling and can offer large heat transfer increases. So here, throughout this, we will demonstrate how implicit geometry can be used to drive the future of heat exchanger design using complex services that provide pretty incredible gains in heat exchanger performance. So we're pretty proud of the performance of this part that we all came together to design and build. So again, this workflow on the left, we start with Topology, working with ANSYS on a simulation-based design process, which was the subject of our second webinar. The first one was our general overview. Then simulation of the actual build and the building process were the subject of the third webinar with ANSYS and EOS. And then the fourth one was looking at the scan to inspect workflow. So CT scanning the part and bringing that into Simpleware software from Synopsys to do that inspection. And then now we're here today looking at the meshing to the analysis of the as-built part, and then also validation through physical testing. So the whole idea of this whole workflow is to reduce risk of poor parts in production while leveraging advanced manufacturing techniques for innovation. So with that, I will pass this off to my colleague Tom, and he will start his presentation.
Thank you, Karim. As my colleague Karim mentioned, that this is basically this webinar is basically a kind of, at least the first part, is an extension on the previous webinar where we used an image-based process to create a 3D computational model of the as-built part so that we could evaluate the as-built part or the build of the as-built part versus the as-designed part and look for any defects or deviations in the as-built part when compared to the as-designed part. Now we want to take it a step further and actually take a look at how the as-built part could potentially perform through the use of simulation. So to do that, we want to use the same image-based workflow to create a model that can be used as the basis for simulations of the as-built part so that we can compare the simulations results to simulations done, the equivalent simulations done on the as-designed part. And to do that, we're going to use the SimpleWare software, which is at its core is a software that is designed to create models from image-based, from images that can be used for this purpose. And just to kind of walk you through the workflow here that we used, we received images of the as-built part from North Star Imaging, which can be seen in this video here. That step through the images. So we got these images from North Star Imaging. There were a stack of images from MicroCT. We imported these images into the SimpleWare software, which allowed us to basically get a look at the opposing views. And we can also use these to kind of take a look and really get a feel for the part and what we would ultimately need to incorporate into our model. We then used the onboard tools in SimpleWare to identify the voxels that correspond to heat exchangers through a process called segmentation, which allowed us to recreate the 3D part in the computational space as seen here. So here you see essentially the images, we segmented them, and ultimately what that produced is a 3D model that can be used as the basis for generating meshes for simulation in this particular case. In this case, we want to do to move a step beyond this, in that we also wanted to take a look at modeling the fluid domains as well and to see if those could be incorporated in a model. So the way we did this is we ultimately did a 3-step process in which we took the body of the heat exchanger, duplicated it, inverted it, and then through using a flood fill tool, we were able to create models of the fluid domain as well as the body of the heat exchanger itself. And what you see here is the final model where you see the model of the heat exchanger and also the fluid domains contained inside it. The next step in the process then is, prior to generating the meshes, we once again wanted to review the images to see if there were any defects in the images that we should ultimately include in our meshes. In this case, the part was very high quality. As printed. We did not notice any visual defects, cracks, or any pores that would ultimately need to be incorporated in our final model. So then we were able just to create a model of the part as it is without having to worry about any of these incorporating these defects, which we did using the SimpleWare software, which gives the user the ability to create high quality tetrahedral meshes of very complex structures and even multi-part structures. The main benefit to using the SimpleWare for multi-part structures like this is that it allows you to create very high quality tetrahedral meshes of all the parts at the same time. And it also will ensure that at all the interfaces, the parts will line up perfectly. There will be no gaps or overlaps, and that the nodes of the elements at the interfaces will match up perfectly. And these can be specified as either coincident nodes or shared nodes at the interface without any issues. The software also allows you to do some post-processing on these orphan meshes to create node sets that can be used as the basis for specifying loads and boundary conditions in the simulation model. So once the model mesh was generated, we then passed this off to ANSYS for simulation, where they ran the simulations to compare performance of the as-built part to the as-designed part. And with that, I'm going to turn it over to my colleague, to Sunil, who will review the process for the simulations and the results.
Thank you, Tom. So as we saw in Tom's presentation, the scanning technology is a great technology to validate if the geometrically intricate complex structures within this additive part have been formed correctly without destroying the part. And that's a great requirement for these sorts of complex parts. But having said that, the mesh that's generated from the scan now becomes a digital asset that can be used for validating that specific part as it was built. Here is an example. You can, when you have these sorts of heat exchanger in aerospace applications, for instance, in a situation like mid-air refueling of this jet plane, the heat exchanger may see elevated pressures, sort of like a surge in the pressure. And we want to make sure that the thin walls that the gyroid structure is using within this heat exchanger is able to withstand those surges in the pressure simply for the structural integrity of the part. And something like that can be easily validated with this scanned mesh, if you will. And here is an example of how you would do that validation in simulation. We brought the mesh in from Synopsys into ANSYS Workbench Mechanical, and it was a flawless operation. As you see that we have applied pressure on the cold side, the one side, similar to what would be done in this sort of burst pressure tests. And the maximum pressure that we're applying is about 6.25 times the operating pressure on the cold side. It's roughly about 940 psi. And also, we are fixing the two inlets and the two outlets or the base, which is kind of like a rigid and probably an overkill, but that's the simulation we've set up. This is a large deformation analysis, and we're going to include plasticity effects. Also note that Synopsys also exports STLs for these. So if you wanted to do something different with the mesh, you have the flexibility to use ANSYS meshing tools with those STLs. For this particular case, we used aluminum's ALSI 10mg alloy properties from the additive materials library that ANSYS engineering data provides. And the specific plasticity was model that was used was bilinear isotropic hardening. So one thing to note about the mesh is we're going to compare now the as-built model to the nominal or the as-designed or the CAD geometry. And we want to make sure that the meshes are similar. And roughly we have about 1.8 million nodes and about a little over 6.5 million elements. Note that the Synopsys mesh is able to get the control for the through thickness number of elements, and we can do quadratic elements to capture the details of the stresses to those thin walls, et cetera, and on top of it, the as-built model, if you see the bottom two pictures, specifically the one on the right, you see features that are not in the original CAD model, but they are a result of the additive process, perhaps some draws, and those are captured very well, both the external features and the internal features, as shown in the two bottom pictures. So to quickly show you the results of this static analysis, at the peak pressure of about 940 psi, we have a max deformation about just under 55 microns, so not very much. And predominantly, the maximum deformation is around the area where the inlets and the outlet of the cold side joins the bulk of the TPMS structure, and everywhere else it's of the order of 10 microns, not a whole lot, right? So similarly, the nominal geometry mesh or nominal geometry design shows that the peak pressure, at the peak pressure, the maximum stress is about 267 megapascals, which is way below the ultimate tensile strength with the maximum plastic strain of the order of 0.4%. And also these maximum stress hotspots are very localized. So it's a very local phenomenon, which may be attributed to local sharp features or perhaps mesh, etc. So again, if I look at the same numbers from the analysis for the as-built mesh for that specific build, I see reasonable numbers. In fact, the maximum deformation, again, in the similar spot to what was expected from the nominal geometry, is just under 50 microns, and the orders of magnitude are very similar to what was expected from the nominal design numbers. Similarly, we see just a little bit lower max stress as compared to the CAD geometry-based model. Again, it's very highly localized, and the plastic strain is very minimal considering the high pressures that we applied. It's just about a little over 0.2%. Now, I talked about those local hotspots for stresses, and in this particular case, the numbers look reasonable at the very high pressures. But if we wanted to resolve them further, there is ability to use something called submodeling. So to avoid large mesh count and the computational inefficiencies that come with it, we can bring only a partial mesh from Synopsys tools and use the global model that with the coarse mesh to drive the smaller model. And that way you could get the resolution that you wanted if you wanted to do further probing of your validation. But overall, to summarize, the as designed numbers and the as built numbers for max deformation, equivalent stresses, and plastic strains are tabulated here. And as you see that the as built geometry passes this validation because its numbers are very similar to what is expected from the original design, whether it's stress, strain, or maximum deformation. There is actually a small improvement, and the only thing we could think of that could have contributed to it is probably the localized thickening in certain areas from the dross in the additive process. Now, this is how a simulation-based validation process would work for a specific structural integrity problem, such as a burst pressure requirement, but also the same meshes from Synopsys could be used to do other analysis, whether it's conjugate heat transfer analysis, as we saw in one of the earlier earlier webinars, or we could bring in more details from the Synopsys scans, where we can bring porosity information, which was absent in this particular build. But for builds that are marginal that have porosity, you could qualify the build for its performance in the field using advanced techniques such as porosity-dependent parts. So this validation process with these meshes works for a variety of situations or requirements. Now, what I have been describing so far is a simulation-based validation. What actually happens in reality? That's the big question. So to answer that, here is Matt from Stress Engineering.
Thank you very much, Sunil. My name is Matt Sanders, and I'm with Stress Engineering Services. And here at Stress, we look to try and solve really challenging technical problems utilizing our expertise in design, analysis, and testing. And so I kind of wanted to start off with a question: why conduct the testing? You can get a lot of good information that you can use to feed back into your design as well as your analysis, but also it helps give you confidence in what you have. An example of that was a part that I tested, a pressure containing tube that was printed via laser powder bed fusion out of a 316L material, and it passed all of the material coupon tests and was printed by the manufacturer per all the recommended settings and passed the QA checks and was handed over as a good part. And even though it was supposed to be able to contain 20,000 PSI internal pressure, at roughly 50 PSI, it started leaking through the wall like a soaker hose. And so that's definitely something that you want to be able to check and know about, and that you can confirm through full-scale physical testing. So we are really excited to be able to be a part of this whole process with the team. And once we received the part, we were really excited to work on it. And there's a number of different types of tests that we do here at Stress Engineering, from material testing, yield and tensile strength, impact, corrosion, environmental exposure, cryogenic testing, flame impingement, shock and vibration testing. We do a lot of fatigue testing, including pressure cycling and thermal cycling. For this part, we did do some flow testing in order to measure the pressure drop as well as the heat transfer, and I'll show you some of those results. And we also did some pressure testing, including a pressure test to failure, or a burst test. And while we were doing that, we were able to monitor the part with our digital image correlation system, which is a way to measure how a material deforms under load, much like a strain gauge. So to give you a feel, here is a diagram of our test setup. And so for this testing, we used a PG1 heat transfer oil as our hot side fluid. And on our cold side fluid, we used water. Now, typically the in the field application may use fuel as a coolant. And although we have used fuel as a testing media here at Stress Engineering, it may not always be practical. And so for this testing, we used water. And so for that, it was important that we took a look at varying and setting up our flow rates in order to match Reynolds number and Reynolds number times Prandtl number, so that we can get some similarity between the full-scale real-world test and the simulation. And so we're able to set up a test in order to simulate field conditions in a laboratory setting where we can control variables, and we can look for certain outcomes and monitor those using different types of sensors. So like for this case, we had various pressure transducers and thermocouples and flow meters on the inlets and the outlets, all running to a single data acquisition system, so that we can record that for all of the tests. We also took some thermal imaging data. Here on the left, you can see the heat exchanger, and then overlaid the thermal image, you can see the hot oil coming into the heat exchanger as well as the cold fluid. Here on the right is where we were flowing just the hot oil and not flowing any coolant, and letting the external casing soak in that heat and become very hot on the outside, shown here. Then when we turned on the cold fluent flow, you can see how much that heat dissipates and the external housing rapidly cools down. And this information can be useful for getting a feel for how temperature is distributed throughout the heat exchanger, and can be used to look back and feed into a heat transfer analysis. So to take a look at some of the heat transfer data, this plot here on the y-axis shows the hot oil temperature decrease from the outlet to the inlet, how much that hot oil dropped in temperature as a result of the cooling water. And that's plotted as a function of the fluid flow rates. And so first we can take a look at this red line, which is where we held the cold water flow at a constant roughly 5 GPM, and then varied the hot oil flow in order to see how that affected our delta T, our temperature drop. And what it shows is that the lower flow rates for the hot oil, we saw a larger temperature drop, which is what we would expect. Conversely, on the other side, the blue line represents where we held the hot oil flow at a constant roughly 5 GPM, and then varied the flow rates of the water. So besides getting some heat transfer data, we also wanted to do a comparison test with the exact same setup. So we grabbed a heat exchanger that we have in our lab, and it's a bit of a more higher performing one. It's a shell and tube heat exchanger, and we wanted to be able to compare them two side by side. So this plot on the left shows the hot oil pressure drop as a function of the flow rate. And what we found is that through all of the flow rates, the newly designed 3D printed heat exchanger had a lower pressure drop, which is a better performance. This plot on the right in the y-axis is the measured calculated overall heat transfer coefficient as a function of flow rate. And what we found is at the higher flow rates, the new heat exchanger outperformed this higher performing older model shell and tube heat exchanger, which was really impressive because even though the new heat exchanger is about half the size in length and almost a fourth lighter than this 4-pass shell and tube heat exchanger. So it performed really well in this comparison test. Moving on to taking a look at the pressure testing. So for this test, we put pressure on the cold side with water at ambient temperatures, and then left the other side, the hot side, full of air, but capped off with a pressure transducer so we could monitor the pressure on that side. We applied the working pressure of 150 psi and held it and showed that there was no leakage, no gross deformation. And then we gradually, incrementally increased the pressure and held it to look for leakage. And we went all the way up to 2,500 psi, or about 17 megapascals. And we didn't see any leakage or any gross deformation. And so we moved on to a pressure to failure test, where we slowly increased the internal pressure until we had a failure. And so we reached just under 5,000 psi, or 34 megapascals, before we saw a large pressure drop. We did not see any external burst or leakage, but we did see at the same time a corresponding pressure spike on the other side, indicating that there was a failure internally and the pressure leaked from one side to the other. So even with that failure, it was so high it exceeded the burst pressure requirement that was 350 psi by over 14 times. So the heat exchanger did well in that pressure test. During the pressure testing, we were able to monitor the heat exchanger with our digital image correlation system. And what that system is it's a pair of stereoscopic cameras that film the test article where we have applied a coating that is a speckle pattern coating where the software can track the movements of the test article and relay how the material deforms under a certain load. We were able to do all of this testing safely inside pressure containment systems to where we knew no one would get hurt. And so the output of the digital image correlation is essentially a color contour plot very similar to a finite element analysis. And this is a video up until the failure test. And what we can do is we can visualize all of the strains across the test article viewing area, and we can pick out different locations of interest after the test and plot those, shown here in this plot, essentially like a strain gauge. However, it's non-contact, and we get a full field representation of the data. And so this plot shows the yellow line with the increasing pressure, the increase in the von Mises strain equivalent that we measure. What we see is a peak deformation right at the inlet going into the heat exchanger body at the same location that Sunil was able to predict in his analysis. So with that DIC data and the test results data, that can be fed back into an analysis in order to reiterate, to modify material assumptions or boundary condition assumptions, as well as relook at the design to make the design a better and more robust. So with that being some of the test results here, I'll turn it back over to Krim for the next steps.
Well, great. Thanks a lot, Matt, Sunil, Tom. Tom, thank you for a nice overview of how you used the CT data for not only the inspection, but then taking it the next step to the meshing and the multi-domain meshing. And then Sunil for describing how you're able to bring those into ANSYS and run your simulations and showing some context of how it's useful. And then Matt showing us some really impressive results with some of your testing. And you were able to turn that around in really short order. So we really appreciate it. So again, I want to thank all of the speakers today and all the previous webinars as well. And we will have our next webinar on June 24th. So that'll be the panel discussion where we'll bring everybody together and have a discussion. We can talk about some of the challenges, how we ran into, how we overcame them, and maybe some of the next steps and some ideas we have. And, you know, we invite you, our listeners, to come and attend. And if you're interested in these types of workflows, contact us. If this is of interest within your organizations, we're happy to discuss them and help deploy them. So with that, I'll end the presentation side, and we'll get on to the Q&A. Thank you. Hi, everybody. Karim here. So thanks for attending. So the question was, what happens when there is a significant amount of porosity, and how is that handled by the meshing? So I guess, Tom, actually that's relevant to the part we showed last webinar, that manifold. We didn't actually get to it in this webinar, just for the sake of time. But I do have those slides. Tom, would you like me to quickly show those, and then you can talk to that?
Yeah, if you would, please. Okay, so, and one thing I should note is that those features that I pointed out in the previous one, they were actually included in the FE model. During the presentation, I actually double checked that, but they were included in the FE model that was Sunil did his simulations on, so could be interesting to see if we had any stress risers in those areas as well. But just kind of like in the case like where you do have, like in that part, because it was a fairly clean part, so it was kind of difficult to detect that you know, defects. But in a part such as this one where you do have a large number of defects, it is possible to include those in the meshing. So if you could go to the next slide, Krim. And the way we would do that is we would actually, when we were doing our segmentation, we would make sure that we would include the defects and the pores in the actual segmentation so that they would be incorporated in the meshing. And the way the simpleware mesher is designed is that we'll actually conform the mesh to actually account for, like as you can see here, all these little defects. So you can see the cracks here as well. And as we scroll through the part, you can actually see the pores here. So the main thing is just making sure that when you're doing the segmentation, that you do make sure that these pores are not filled in, because if they are important to the model, you want to make sure that they are present, and then the software will take care of it, and will actually, as you can see here, refine the mesh around the pores so that they would be incorporated in the model. And as you can see here on the next slide, that why is it important to do this? So if you look at the CAD-based model on the left and the image-based model on the right, we do see that there is a difference between the two results, in that you have basically in the CAD-based model, you do see the stress risers above that hole or opening on the kind of towards the right-hand side, but in the image-based model, the stress riser actually moves down and actually kind of starts to impinge on the open hole, kind of more towards the center of the model.
Great, thanks, Tom. So, sorry, Sunil, is that something you want to add to that?
Yeah, so just a comment here about this approach, that in this particular analysis, we actually meshed the minor defects, and those minor defects could raise the stress concentration, and that's what you're seeing. The other way the pores come into play is that the effective material properties of the material is changed, and there are material models that account for this kind of relationship between the voids and the material properties that it has. So another way of doing this is also, as it says in the last bullet point, is there is a way that the Synopsys tools can export porosity through the entire field for that part, and that can be brought in very easily into ANSYS, and then use that in analysis with more advanced material models. And that has the advantage that you can work with a much smaller mesh, and also smaller mesh size, and also it's really more accurate in terms of you don't have to worry about trying to figure out if a stress is there because of a sharp object or a sharp corner, whatever, so resolving stress becomes a little more meaningful in that approach as well. So really, there is a lot you can do with these approaches.
Great, thanks, Sunil. Another question was, how does ANSYS handle STL files from Synopsys or from NTOP during the initial design stage? So I guess that's for you, Sunil. Maybe you, Tom, also once you get the images.
Yeah, so we do have STL-based meshing in several of our tools, and that's pretty straightforward. You've seen during this webinar series, we've shown you tools in Discovery, our Discovery platform. We've shown you analysis with Mechanical and also Fluent. In all of them have different capabilities to handle STLs. In Mechanical, we have improved the STL-based meshing capabilities specifically for these kind of applications coming from additive. But overall, I would say the best way to do that, or the most cleanest way to do that with a lot of control, if you are into meshing with details, then I also recommend something like Fluent Meshing, which has great capabilities for STL.
Great. And a question for you, Matt. Have you planned also to perform cyclical testing and high temperature tensile testing?
We don't currently have that planned in this scope of work, although I'd love to be able to do that on this part. We could have a test rig where we can apply cyclical pressures from, say, 0 up to the operating pressure, thousands or 100,000s of times. It'd be really interesting to see how fatigue affects some of those internal cavities with the surface finish from the 3D print. And then we can also do that at elevated temperature. So that's not necessarily in the scope of this, but would really hope or get the chance to be able to do that, as well as potentially a full burst test of the external housing. The failure that we saw on this part was internal, and so it's always more fun to get to blow something up. So.
Great. All right, well, we just got quite time for one more question. I think this is for you, Sunil. Did you compare DIC results with image-based simulation results?
That would be an interesting task, and we would certainly like to do it. As Karim alluded to, a lot of this testing that Matt performed was done in the last 2 days, and we had the part scanned last night after it was filled. So yeah, we would like to do that. I would say a couple things that the analysis maybe needs to done. There might be slight change in approach if we want to match the analysis to the DIC correlation completely. We've seen from our existing results, just looking at it from 10,000 feet, that it has a lot of similarities in terms of where the hard spots are, and also the level of magnitude of the strain. So that part we are pretty comfortable that they match. What's important to know is that in the simulation, we fixed the 4 legs at the bottom completely, and in a way that was overkill, but it simplified the simulation time for static simulation, as you can imagine. But it also creates a situation where you create additional stresses, and so from that point of view, there might be some ways you can do the simulation slightly differently, or do modifications in a way that allows you to match or have more of an apple-to-apple comparison with the experimental results.
Okay. Well, great. Thanks, Sunil. And thanks everybody who presented and who attended. We really appreciate your time and attention. And for those who we had a bunch more questions we didn't get to, and we will try and get back to you over email as soon as we can. And in 2 weeks, we will have the panel discussion where we're going to bring everybody together, so we can have kind of a more holistic discussion about this whole workflow, because it was, obviously it was piecemeal by intention to really try and educate you on each step of the process. But then the next step now is to kind of take a step back and look at the whole workflow and see how, different companies might have different interests in different parts of it. And we'd like to address all that. So with that, I'd like to thank our speakers, and we'll see you in 2 weeks.